Moving right along with modeling motion, we're going to look at first in a series of videos on variable forces, and this one is establishing some acceleration expressions. If we have variable forces, we invariably have variable accelerations. So what I mean by that is a variable force means a variable acceleration, okay, if we go to Newton's second law. And we have some things we might have established here earlier on. What we're doing actually in this video is we're coming up with some expressions, 4 in total, 3 to 4, and basically they're what we use when we don't have a constant force, because all the previous videos have been related to various sorts of arrangements of forces and various manifestations, but the forces each have been constant. That's not always the case, so let's look at variable accelerations, which will lead us to variable forces coming up. And as I was just saying then, you should already know from your mathematics studies that acceleration A is dv dt, the rate of change of velocity with regards to time, or the second derivative of displacement, okay, and with regards to time, and you can see that there. That's something that you've seen already. If we apply the chain rule to dv dt above, we can say dv dt is dv dx dx dt. And that can be written as dv dx, and the dx dt right there is also known as velocity. So it's dv dx times v. So that means an expression, a valid expression, could be written as acceleration is, because this is all acceleration, acceleration is v times dv dx, if we just swap that commutative order around. So there's one key result. Likewise, using the chain rule, we could manipulate that chain rule, manipulating in particular the v part. So this would be like an application of the chain rule. Now the dv dx, I'm just going to write that aside here, and the work's going to be done on the v. It is possible to rewrite v as d dv of a half v squared, because if you took the derivative of that, you'd have back 2 on 2 v to the 1. 2 on 2 v to the 1 is just v. The cancelling like effect using the differentials would give us d dx of a half v squared, and that's another useful form. That's where they come from. So let's summarize this. We have 4 terms in total if we include these 2 earlier ones. So if we have certain functions, so they're all to do with a, of course, that's what this video is about, but these are a as a function. Now variable acceleration means it's a function of something. We can have acceleration as a function of time, acceleration as a function of velocity, acceleration as a function of displacement. There are 3 situations you should be prepared for. Variable accelerations can be due to time, velocity, and displacement. So if we have in the first row, if we look across, if we have the function in the form of a equals f of t, the initial conditions might be provided in a question in terms of time and velocity. Use good old a equals dv dt. If we have a equals in the second row a function of velocity, and initially we're given time and velocity, again use dv dt. However, if we're given in the third row, again a equals f of v, a function of v, but we're given displacement and velocity, we can't use dv dt. We use what we established above there v times dv dx. Lastly, we do have the option, if we've got acceleration as a function of displacement, one way of doing it is, and we're provided with x and v, one way of doing it is what you see there. This last one's not always necessary. Let's look at one example. There'll be more to come in other videos. Now in this video I don't claim that I'm going to show all of those examples above in this particular video. It'll make it run too long, but I will be showing two ways of doing one particular case here. So an object travels in a line such that the velocity in meters per second, which we'll call v, is given by v squared equals 4 minus x squared. Find the acceleration at x equals 1, assuming meters there, okay, because the velocity is given in meters per second. Now just going back to what we looked at, if we look at the last two rows here, I'm looking at in terms of x and v has caught my eye, because we are given an expression in terms of x and v in the initial conditions, okay. We're not given any such function yet, but looks like it's going to end up using one of these two here, okay. So there's two ways of doing it, and in fact both of these can be used here, and these are often interchangeable. Probably the third one gets used more, and it can displace the need to do the last one, but I'll show you anyway. So if we decide to use implicit differentiation, okay, so that's from previous work. Implicit differentiation is one way of going about this, and that means we're going to take d dx of both sides. So d dx of v squared equals d dx of the right hand side, which is 4 minus x squared. Okay, so we've got 2v times dv dx. On the right hand side we've got negative 2x. And look, we've got the expression for acceleration v dv dx if we divide both sides by 2, and that would leave negative 1x on the right hand side. So remember, v dv dx is our expression for a, so we can replace that with a, and we've found the expression for acceleration, okay. And at x equals 1 we were asked to find that acceleration. It doesn't like doing that. It thinks I'm trying to lasso something. Aha, that's an at. Alright, so at x equals 1, and we sub in 1, so the acceleration is negative 1 meters per second squared. Okay, and the other way of doing it is to consider the final row in this table. If we can look at d dx of a half v squared. Now we haven't got a half v squared, but if we halve both sides, we do. Half v squared is 2 minus half x squared, and that's a, if we take the derivative with regards to x. So let's do that. Okay, now that's the expression for a, acceleration, and we need to do the same to this side here. Like so. A little bit untidy there, sorry. That's a squared. And that's a. And taking that is easy because we just get negative x again, because the 2, net minus 2 on 2, x to the power 1, which is just negative x, and we just sub in x equals 1 again, so a equals negative 1 meters per second squared at x equals 1 meter.